Who's the next? Sorry, and the next speech now. Oops, my time has run out. Right. Oh, and the next speech is a teacher in Cuba. This is called the Implementation and Operation and Localization and Assignation for the Analytical Model for gvSIG networks. Right, as mentioned, this work is called Implementation and Operation Localization for the Analysis Model of gvSIG. It's work which has been developed in our university, and the presentation is divided into motivation, introduction. Then we take a look at the networks. Then we'll explain what is the problem with localization and assignation. We'll show then the design and the implementation of the tool and, well, some elements of the implementation itself. And then we'll reach the conclusion stage. So we begin with motivation and to take better strategic decisions. There's been a group of tools which have come out, which algorithms which enable us to make distributions using networks, different types, networks of different types. So it's useful to understand better. So the dynamic markets, the movements which exist in certain city, and sometimes we don't have enough data, like spatial distribution, which could be useful to us to be able to resolve a particular problem. We all know and are used to using the tools which exist for network analysis with Google, which are free, but in some countries and some places, Google cannot be used. The Google tools cannot be used. For example, in Cuba, for example, we've tried to develop a set of algorithms and to provide a solution to the problem of localization and assignation for transport networks in this case, and one of the version of gvSIG. So we use the method optimum localization and installations and services, and we have the suitable. And if we have the suitable information, we can get interesting analysis. And using this type of algorithm, some of the information system, geographic information systems, actually presently incorporate this, which geographic information proprietary. We take a look at this type of algorithms. So we take a look at in the geography, in a bibliography, and we find some software. We see some of it has got this type of tools incorporated, and we realize that in gvSIG, the network model when it came out incorporated some of the basic things, but this specific one it didn't include. There was no way to implement it. So there was difficult problems difficult to resolve in the process of decision-making process and in town and regional planning, and this tool could be useful to try and resolve these problems. So we need to develop them in a suitable way to be able to treat this type of problem. We take advantages of integrating the models of localization integration, so we can have a visualization of this, and to be able to calculate automatically what would be the solution to a specific problem, taking into account the distances which can exist, the problems we have. But here in this case we're talking about transport networks, so the aim is to extend the module of gvSIG networks using the incorporation and of the operation, localization, assignation to carry out new analysis on transport networks. So we talk a little bit about type of networks. We talked about the transport networks are not directed in this case. There are other service networks which are directed networks. We have certain software which is very powerful in both types of, well, in one or other type of network. In this case, we can analyze transport and variables in transport networks. In this case, one of the most powerful. Not many companies have the possibility to have the licenses because these are quite expensive. The licenses for these tools, for electricity, for example, for water, or for oil pipes. Traditionally, some of these are used on transport networks. In this case, we're talking about the best route, which we use it almost every day in a developed company. Using the same telephone, how can we calculate the best route using the tools which exist and are available and are free? With the ease of closeness. In this case, if there is a certain incident, for example, or we need to get to a hospital or to a police station, we can calculate by distances. Especially we can use the network itself. We can quickly. Somebody can easily be attended then by a particular service, in this case, service areas, which are type of problems which enable coverage in a certain point for it taken into account. Impedance based on distance, basically, or time also. And how long does it take us to get from one place to another place? And which place could we reach to provide support for a particular need for a certain client who is asking us for the service? We need to take a look at the matrix of the cost of the origin of destination, which is one of the tools which is going to provide us a graphic information and data in a table, and also the different routes the vehicles take, which are quite variable. They're considered quite complex to calculate these. In these cases, we're talking about a fleet, for example. We have a fleet of transport fleet. Well, we've got a deposit and in the depot, and from this depot we do a distribution in a time frame, for certain hours during the day, for example. And how we satisfy a certain number of a group of clients in an easier way, and optimizing the resources, which could be time, distance, in the end, petrol, and this is going to fuel, and which could be a great problem for many companies. And finally, the problem with the localization assignation, which has got a use. So I'll talk a little bit more about that a bit later. Let's take a look at, here's a classic example of the best route. How to go from one place to another. The best route doesn't mean that it has to be the closest route or the shortest, or the most, or the prettiest, or the one in which I save more fuel, more petrol. This would going to depend, of course, on how you calculate things. This is just one example. We've used this is one of the tools that have been implemented in the network analysis in gvSIG. So it was tried out, and we're talking about the closest facilities. We could arrive, for example, at hospital, which is the closest hospital, or where there is less traffic, and we could perhaps save somebody's life. And then when we talk about the facility, the closer facility is also implemented here, as we can see in gvSIG. In the case of service areas, the service area solver, I said, how we get from one particular point, for example, where we have a service for delivering pizzas, which is the area in which we could provide an answer to certain clients in under 10 minutes, which routes we have to take, which roads we have to take. And take a group of factors, and we can find out what this area is. We can calculate it automatically, working on the actual nodes in the network. Well, there's an example of the service area. In this case, This is in Seville. We talk about the costs at destination, origin and destination. And we take a look here at all the points and the time which this could take, and different attributes which are related to the points which should be interesting for this problem. We're going to take another example here. Here we've got a vehicle. Imagine we've got a depot here, and we've got a fleet. We've got 3 cars, or 3 however you call them over here. We've got a certain capacity for production capacity which these cars can do in a certain time frame, and obviously we've got an awful lot of problems here. We've got a time frame. How can we provide solutions and cover with the resources which we have? How can we cover all the existing demand of the clients? Here we can see another example about the city of Seville. And here we've got a problem with localization assignation, which deals with how we can assignate or designate different points of demand to a set of service points, not only localization assignation. If we take a look at this type of problem is related to 2 sides. One is the optimum localization of the system, and the other is assignation of the points of demand points for these services. So we could divide this up into various problems, several problems. What we try to do is we deal with the problem of minimizing the weight, which focuses on minimizing the distances from the point of demand from the point of service, which is assigned to each of these. And the codes are trying to maximize the weight, which the addition of these will be maximum. And when we try to minimize services, we try to get the addition of the distances to be the maximum. We also want to minimize services, want to assign the demands in a way that... Here we've got some examples of 3 examples of use which were implemented here. Over 1.11 version of SIG, which incorporates a module for network analysis, where we have some functionalities. We can generate a topology for the network based on GPS, which is lineal. We can load a file, generate a .NET file, which once it's been calculated, and we've got all the nodes, we've done all the calculations, the graphic calculations, based on the original geometry, when we can incorporate a minimum field, the service area, the closest event, the cost matrix, the origin, destination. We also have localization assignation, and in this case, something which was quite easy to do. We used a panel where you could choose the service layer, for example, public schools, primary schools in Seville, and the demand layer, centroids we have here for all the city. And we can also have the field for the number of services. We could have the impedance and the type of problem we want to look at, to tackle. To do this calculate, we used genetic algorithms. Genetic algorithms were based on populations where you can quantify the problem using, and the solutions would be the codify a HIM. The genetic algorithm can be used with a population. In this case, we worked with chromosomes. 500 chromosomes we work with, where the solution would be general chromosomes, and we can make different iterations with this until we get an acceptable result. Repetitions with the amount of genes for a particular chromosome, if they can coincide with the quantity of points of demand. And the admissible values for each gen match up with the quantity of service points. So the solution would be could be 1,000 iterations. We have repetitions here. We'll take a look at the impedance of the problem, and we're going to end up with the best solution, which is going to be viable through the network. So we got the rate, the gene rate, tells us the demand point, and the value indicates the service point. If we did a comparison here, and the results were equivalent, the same in this point, to what they did with ArcHIS in Seville and gvSIG, and the algorithms, the genetic algorithms for this problem, gave the same graphic solution, and also for minimizing impedance. So this incorporated the operation of localization assignation to the module of gvSIG networks, and with this way we were able to carry out new analysis. And we just found out the results of the developed tool for gvSIG with the ArcGIS have the same examples with the same answer. With future work, we can implement all types of variants which is possible for the localization assignation problem. We can develop other problems about analysis of transport networks using gvSIG. Thank you very much.
Muchas gracias.